Good morning, all. In the last class, we have discussed the different terms associated with the phase diagrams, what actually a phase means, components, degrees of freedoms, etc. And also, we have discussed the invariant equilibrium, monovariant equilibrium, divariant equilibrium, etc. In today's class, we will discuss the classification of phase diagrams and what actually a phase diagram means, and different rules which is governing to find the phase fraction as well as the composition of phase in a binary phase diagram. Okay, so phase diagram actually it is a graphical representation of combination of the temperature, pressure or composition over two axes. Okay, the diagram actually shows the relationship between the phases which are in equilibrium when we are varying any two parameters. Like example, if we are varying the temperature, what will happen to the phases? If we are varying the pressure, what will happen to phases? Or if you are changing the composition, what actually change in the phase of a particular material? They are also called as equilibrium diagrams or constitutional diagram because the phase existing in these phase diagrams are in equilibrium. So it actually shows the relation between equilibrium for a corresponding particular temperature and corresponding particular composition of a alloy. So when we are classifying this phase diagram, it can be classified based upon the number of components present in it. So the type of phase diagram actually it starts with like unary phase diagram, binary phase diagram, ternary phase diagram, quaternary phase diagram, depending upon number of components involved in it. And when we are comparing the parameters, the main three parameters which are involved are temperature, pressure and composition. And except the unary phase diagram, for other phase diagram we will be intentionally avoiding the parameter which is the pressure. As the modified form of the Gibbs phase rule, we will be ignoring the pressure as a measuring parameter. So we will be considering only the temperature as well as the composition variation. But in the case of unary phase diagram, we will be also considering the pressure as a parameter. Okay. So the first classification of phase diagram, unary phase diagram. The well-known example is the water. In the last class we have discussed like water is an example for monophase or a single phase material. So when we are considering the water, it can exist in three phases. We know a phase actually represents a species which is having a physical homogeneous properties or chemical homogeneous properties. In the case of water, if you are considering the three forms as water vapor, ice as well as water, the solid, liquid and gaseous forms, all these three will be having same chemistry or same composition of H2O, but ice will be having a particular physical properties and it will be throughout the entire range of ice. Water will be having a particular homogeneous properties and water vapor will be having a distinct property which is different from the ice as well as the water. So all these three can be considered as three phase. So in the case of water, as mentioned earlier, pressure is considered as one varying parameter for constructing the phase diagram. So actually a unary phase diagram of water, it consists of a two parameters, pressure as well as temperature, on which we will be plotting the variation of the phase. In the water we will not be having any variation in the composition, hence we will be ignoring the composition axis. So throughout the entire three phase, all the composition remains same, which is the H2O. So there is no composition axis or the variation in the composition. So two parameters, pressure as well as temperature is plotted. Pressure is plotted on the y-axis, temperature is plotted on the x-axis, and we will be measuring the variation of temperature with respect to pressure, how these phases will transform from one when we will be moving from one temperature to another, or when we are moving from one pressure to another. And there is one particular point at which all the three phases will be coexisting in equilibrium, which is called as the triple point of water. It occurs at 0.0006 atmospheric pressure and 0.01 degree centigrade temperature. Okay. So unary phase diagram is beyond the syllabus, but for the sake of understanding, we have discussed like the classification of phase diagram starts from unary phase diagram or single component phase diagram, and water is a well-known example. So when we are coming to the scope of the syllabus, the first classification when we are considering the phase diagram, it is the binary phase diagram, which consists of actually two component system. So binary phase diagram can be again further classified into two. The first one is binary isomorphous diagram, second one is binary eutectic diagram. So one basic understanding required is like the classification of phase diagram, it comes from the number of components present in the phases. It is not based upon the number of phases, which means the unary phase diagram is the particular phase diagram which consists of a single component, which is the water. It is not depending upon the phases. If you are naming it is based on upon phases, it already consists of three phases, which is solid, liquid and gaseous form of the water. So when we are classifying the phase diagram, the unary, binary, ternary or quaternary, all these classification came based upon the number of components based in the system. So in the case of unary phase diagram, we had one single component, so it is called as unary phase diagram. When we are coming to binary phase diagram, we will be having two components, so we are calling it as binary phase diagram. And the binary phase diagram again can be classified into two, which is isomorphous diagram, second one is eutectic diagram. That classification actually depends upon the solubility of these particular phases. So if the two not the phases, the components, if the two components which is added to form this particular alloy or solid solution, if it is having complete solubility, we will call it as isomorphous material. So the binary isomorphous phase diagram is the particular phase diagram in which the two components will be having complete solubility. The component A will be completely soluble in component B, and component B can be completely soluble in component B. In the second case, when we are considering the eutectic system, that is the condition where the component A as well as component B are having a limited solubility or no solubility. So it will not be completely soluble. That particular class is called as eutectic system. So eutectic system can be again further classified depending upon the solubility limit. One system in which the materials are completely soluble in solid state, or the components are completely soluble in solid state, but it is completely soluble in liquid state and completely insoluble in solid state. That is one classification. Another classification is components have complete solubility in liquid state but has a limited solubility in the solid state. So the first example is the binary isomorphous diagram, and the well-known examples for the first classification is the binary isomorphous diagram, and the well-known examples are copper nickel alloys, germanium silver alloys, silver copper alloys. All these materials are actually, if you are considering the copper nickel binary phase diagram or binary system, we know copper is one component, nickel is another component. Copper and nickel, when we discuss the classification of solid solution, we have discussed this two elements or these two alloys, copper nickel alloys, as an example for substitutional solid solution. At that point we have discussed like these two systems are having complete solubility. So it is one example for the binary phase diagram, copper and nickel. So copper can be completely dissolved in nickel, and nickel can be completely dissolved in copper in its liquid state as well as in the solid state. What actually means by this term, in liquid state and solid state, which means when we are heating the material copper as well as nickel above its melting point, in the molten state these two are completely miscible, or these two can completely miscible. We cannot separate these two once it is mixed in the molten state, and once it is solidified or when it is converted from its solidification temperature to room temperature, it can again retain that mixed condition, or it can again return as a single phase which cannot be separated. That is the meaning. It have the mutual solubility in the solid state as well as in the liquid state. Normally any material its liquid state, we can mix two material, but when we are comparing to solid state, or when we are cooling it into solid state, the material will be having this limited solubility, and the excess material will be precipitated out. But for the isomorphous systems, the two materials or the two components will be soluble in liquid state as well as in the solid state. Okay. So the figure shows the actual representation of this binary isomorphous diagram over a two axis, a 2D representation in which left axis or the y-axis represents the temperature and the x-axis represents the composition or in the weight percentage of nickel. So next is how to construct this binary isomorphous diagram. How we will be creating this binary isomorphous diagram. So in order to construct a isomorphous diagram, what actually we require is we requires the melting point of the two material, melting point of the copper as well as melting point of the pure nickel. So as in the figure we can see over the y-axis we are representing the temperature scale, and the x-axis we are representing the composition axis. So if you are considering the extreme left position, you can see it is 0% nickel. As the axis you can see it is represented as weight percentage of nickel, how the nickel is varying from 0 to 100%. So as it mentions 0% nickel, it actually means that it is having 100% copper. So extreme left position or the origin of the phase diagram, we can say it is 100% copper, which is on the extreme left side, and upon the extreme right side we can say it is 100% nickel. So when we are moving from left to right over the x-axis, we can say the concentration of copper is getting decreased, the concentration of nickel is getting increased. That actually we are representing as the weight percentage of nickel. So nickel is varying from 0 to 100% over the x-axis, which means correspondingly the copper is decreasing. For example, if you are considering a point at 40 in the x-axis, this actually the point 40 in the x-axis actually represents 40% nickel and 60% copper. And if you are considering point 80 in the x-axis, 80, that particular point's composition actually represents 80% of nickel and 20% of copper. And extreme right end, which is 100 actually represents 100% nickel and 0% copper. So in a phase diagram, we can say when we are telling a binary phase diagram, one component will be varying over the x-axis. Okay, at the extreme two components we will be having the parent material. Okay, so the left end actually represents 100% copper or the pure copper, right represents 100% nickel or pure nickel form. Okay, so next we are marking the melting point of the copper. So pure copper is represented on the left extreme end. So in the left axis, left y-axis, we are marking the melting point of the copper, which is 1085 degrees centigrade, which is already marked on the particular axis, y-axis. In the extreme right hand y-axis, we are marking the melting point of the corresponding element B, which is the nickel. So melting point of nickel is 1455 degrees centigrade. So we will be marking the melting point over the y-axis on the right hand side. We can ignore the scale in the degree Fahrenheit, that is not required. So already we have mentioned the scale over the left side, which is in degree Celsius. So degree Fahrenheit scale, it is not mandatory. So now what we have is like we have two axes, x-axis and y-axis, and in x-axis we have marked the variation of nickel from 0 to 100%, and over the y-axis we have mentioned the melting point, the temperature over the particular variation in the scale, and we mark the melting point of the two material, the copper as well as nickel, over the y-axis. Next you can see two lines actually, one lines actually considering as a boundary between the complete liquid phase and the inner white phase, which is actually liquid plus solid phase. So one boundary which separates the liquid phase and the liquid plus solid phase, and another boundary which separates the complete solid phase and solid plus liquid phase. Okay, so that in the particular phase diagram you can actually identify three regions. The region above the particular line called as liquidus line, it is called as complete liquid phase, and the particular region below the solidus line we will call it as complete solid phase, and the region which is marked as white color, which is alpha plus L, actually represents the inner white region, which actually inside the liquidus plus solidus line we will call it as liquid plus solid phase. Okay, so three regions can be identified over the phase diagram. One is complete liquid phase, which can be also represented by L, and complete solidus phase, which can be also represented by the alpha. So alpha actually represents the solid phase, L represents the liquid phase. So inner region actually consists of alpha plus L, which actually means it is a two-phase region which consists of solid and liquid phase. So this is the particular phase diagram, which is the binary isomorphous phase diagram. We know we have regions which is completely liquid, we have region which is completely solid. The liquid phase actually it is a single phase region. The solid phase is actually a again single phase region. The liquid plus solid region, which happens inner the solidus plus liquidus line, we will call it as it is a two-phase region which consists of molten liquid as well as solidifying solid parts. Okay, the line which passing through connecting all the boundary between the liquid and liquid plus solid phase, we will call it as liquidus line. The extreme boundary which separates the solid phase from solid plus liquid phase, we will call it as the solidus line. So these are the different terms which is associated with the binary phase diagram. Okay. So the three different phases we can identify: liquid phase, solid phase, and two phase region which is the liquid plus solid phase. So what information actually we will get from this particular phase diagram or this particular binary isomorphous phase diagram? We can understand the phases that are present. That is one important point, and also the composition corresponding to that particular phase. Third is the relative percentage of phase which is present. So three important terms we can obtain from the phase diagrams are number of phases present, the composition of the particular phase, and the relative percentage of this particular phase. So by number of phase we can identify like whether the solid phase or liquid phase or liquid plus solid phase. That is actually infers to the number of phases. The composition of this phase actually represents, in if you are considering one phase, in that particular one phase how much amount of copper is present, how much amount of nickel is present. Okay, that actually means by the composition of the phase. And if you are saying the relative percentage of phase, from that it means if you are considering a particular phase, in that how much amount of solid phase is present, how much amount of liquid phase is present. For example, if you are considering the inner region where liquid plus solid phase we are having, in which how much contribution of liquid phase is there, how much contribution of solid phase is there. That is the relative percentage of phase. So next we will discuss how to find this composition. Okay, so already we know in a binary isomorphous phase diagram we will be having two phases. So liquid phase is there, solid phase is there, the region of liquid plus solid phase is there. So if we are considering the inner region, the liquid plus solid phase, and if we want to determine the composition of this particular phase at a particular temperature, so what we actually do is like we will draw or we will project a horizontal temperature, horizontal line corresponding to the required temperature where we have to measure the composition of phase. So this particular line is called as tie line. So for example, if we have a temperature, for example 1200 degrees centigrade, so we will be projecting a line corresponding to 1200 degree, which so that particular line will cut the two lines, which is the solidus line and the liquidus line. It will cut the liquidus line at point X and solidus line at point Y. So we will be having a straight horizontal line which is XY, which is passing through the liquid plus solid region, so which is called as the tie line. So it is drawn across the two phase region. The intersection of these line with the phase boundaries on the both sides are noted. So then what we'll do is like we will be dropping a vertical from the 2 points, from X as well as from the point Y. From X we will be projecting to the X axis, and we will get a particular composition in weight percentage of nickel. For example, if you are considering the copper nickel, it will be in weight percentage of nickel. So that particular composition actually is the composition of liquid phase inside that liquid plus solid phase at that particular temperature. Okay, so for example, if we are projecting from x and over to the x-axis, and we will get like percentage of nickel as 40%, which means at the liquid phase at that particular temperature in the inner region will be having a composition 40% nickel, 60% copper. Similarly, if we are projecting from y and if we are arriving at x-axis at a particular composition, for example 50% nickel, it means at point y, sorry, in that particular inner region we have the composition of solid as 50% solid and 50% copper and 50% nickel. Okay, so this particular tie line actually is used for finding out the percentage of composition or the composition of the particular phase inside the liquid plus solid region. So the percentage of solid phase, how much is the composition of solid phase and how much is the composition of liquid phase. Okay, so tie line is used for determine the composition of the liquid phase as well as solid phase inside the liquid plus solid phase region at a particular temperature. Next we will be discussing the so now we know the composition of this particular phase, like in the inner region we know what is the composition of liquid phase and what is the composition of solid phase at a particular temperature. Next what we need to find is how much contribution of solid phase is there and how much contribution of liquid phase is there at a particular temperature. That actually is represented by the relative amount of phases. For example, we have like 20% at a particular temperature, we have 20% solid, rest 80% nickel, or 50% solid, rest 50% nickel. So we need to know how much is the quantity, like quantity of solid or the phase fraction of solid or phase fraction of liquid present in the two phase region. In order to find that, we will be using a rule which is called as lever rule, or also known as it is a lever line. So again we will be drawing a tie line as mentioned earlier. From a particular temperature we will be drawing a horizontal line so that it will intersect the 2 points x as well as y. And now what we need to know is, like, over this xy, if we are considering any particular point, we need to know how much amount of liquid or how much amount of salt is present at that particular point. So for arbitrarily we will be considering one point which is point M. So this M actually lies on this particular tie line xy. So now what we do is, like, similar to the previous condition, we will be projecting from M a vertical line towards the composition axis to find the composition of M. So now what we know is actually the composition of x we already know, composition of y we actually know, and we will now know the composition of M also. Okay, so next is a particular formula to find out the phase fraction, or the fraction of liquid phase or the fraction of solid phase. So the relative amount of phase, liquid phase, it is actually obtained by measuring the difference between the composition of the y subtracted from M. So the difference between the M and Y divided by the total XY length. So in terms of the percentage, which means it is the composition of Y actually is, it will be CS, the composition of X actually it is CL, the composition of M actually it is the C0. If we know the three composition, the fraction of liquid actually it is represented by CS minus C0 divided by CS minus CL, which actually is the length of MY divided by XY, the total length of the tie line. Similarly, if we want to know the relative phase fraction of the solid phase, what we used to do is, like, we will be in numerator we will be having the XM, in the denominator we will be having the total length of the tie line, which is the XY. So MX by XY is actually giving the phase fraction of the solid phase, and in terms of composition we can rewrite it as C naught minus Cl by Cs minus Cl, where C naught represents the composition at point M, Cl represents the composition at point X, and Cs represents the composition at point Y. So by this we can easily find out the relative percentage of solid phase as well as the liquid phase present inside the material. So by tie line we know the composition of the phases, by the lever rule we know the relative fraction of each phases, the solid as well as liquid phase. And these rules exclusively it is associated for the isomorphous diagrams. Normally for the other kinds of diagram we will not be following the tie line and lever rule, but for the binary isomorphous diagram we can find easily the relative percentage of the phases as well as the composition of the phases by using tie line and lever rule. Okay, so we already discussed like the binary isomorphous diagram, the how we can represent the binary isomorphous diagram with the different phases, liquid phase, solid phase, and the liquid plus solid phase. Next we will just brief how we are constructing this particular diagram. We have seen the liquidous line, we have seen the solidus line, but that particular curvature of liquidous line we have seen, that curvature of solidus line we have seen, but how we actually constructed this diagram, we will be seeing the background of this particular diagram over here. So what actually we used to do is, in order to create any phase diagram, what we actually do is we will be making different alloys, metal alloys of that particular composition under which we will be considering for the phase diagram. For example, in this particular case, we need to construct a copper nickel phase diagram. So what actually we used to do is we will make different alloys. For example, in the initial case we will be having a pure copper material, we will be having a pure nickel material. Then what we will make is we will make a alloy of 20% copper and 80% nickel. Then we will make another alloy of 40% copper, 60% nickel, then 60% copper, 40% nickel, 80% copper, then 20% nickel. So we have at least 5-6 elements of different composition. Okay, so next what we used to do is we'll construct the cooling curves for these alloys, or we will do the thermal analysis for these alloys by melting and solidify. So we will heat all these alloy above its particular above its melting point and then solidify it separately. So first we will do the melting and solidification of copper, then melting and solidification of nickel, then the different alloys. So and what we actually obtain when we are doing this process is the cooling curve. Like initially what is the actual melting point of that material, then when we are drawing the cooling curve upon cooling, what actually happened to that particular phase. If you are considering the pure material copper as well as nickel, we can see the point AB and points CD actually represents the corresponding melting point. So melting point or the phase transformation of that particular pure elements. But when we are considering the phase transformation of alloy, we can say it is a slanting line. So that points the point A, the point L1, point L2, point L3, point C, all these points obtained is connected to draw the liquidous line, and the point B, point S1, point S2, point S3 and point D all are connected to draw the solidus line. So actually we will be melting and solidifying different alloys, and we will be noting down the corresponding melting points of all these alloys, and we will be connecting all these lines to obtain the liquidous line and solidus line, and thus we will be getting an actual phase diagram which we already discussed previously. So this is how experimentally we will be constructing the phase diagram. By we will be making different alloys of different composition, and we will be finding out these phase transformation temperature of these alloys, and we will be connecting these points to obtain the liquidous line and solidus line, and we will be making the final phase diagram or the binary isomorphous phase diagram. Okay, by joining all these liquid solid transition temperature for various composition, we will get the continuous curve which indicate the phase boundaries. Okay, that is all about the construction of the phase diagram. Thank you.